Okay, good morning, guys. Today we're going to be starting our last section before our test. Our test in this case this year is going to be after Christmas break, unfortunately, very shortly after we get back. However, we're going to be talking about optimization problems. But before we do that, let's get the juices flowing here. And let's find the function f of x whose derivative is x squared plus 4x minus 6. And I know f of 3 equals negative 2. So what that means is, right here, remember that's f prime of x. So if I know f prime of x equals x squared plus 4x minus 6, you want to find its antiderivative. Why don't you hit pause and find it, see if you're right. Okay? Well, that means f of x, actually, x squared has to come from a cubic, and I need a 1 out front of that squared, so I'm going to throw a third in front of that. Plus, I know 4x to the first comes from an x squared, and I need 2 times something to get that 4, so I'm put a 2 there. Constant, antiderivative of a constant would be a linear function plus c. Okay, so what that means is any function, okay, there's an infinite number of them, there's a special number c, there's an infinite number of functions whose derivative actually is x squared plus 4x minus 6. We want the specific one that is going to be going through the point 3 comma negative 2. Well, then all we do is we come back and we're like, whoa, well, okay. What is c then in this case? Well, I know y is negative 2, and I know that negative 2 comes from when I plug 3 in. 6 times 3, and I find that c. So first thing I'm going to do here is I'm going to say, okay, negative 2, well, that equals, well, this third is going to get rid of one of those 3's and make that a squared, right? Because that's 3 times 3 times 3. So I get 9 plus 9 times 2, that's 18, minus 18 plus c. Well, I can see those 18's go away. So c must equal negative 11. Well, remember here, because c equals negative 11, my specific solution, f of x, is going to be 1/3 x cubed plus 2x squared minus 6x. c is minus 11. This is my specific solution that goes through that point, f of 3 equals negative 2. And before I got there, this is my general antiderivative. Okay, that's the general one because there's an infinite number of functions whom have that derivative. That's why with the c, that's the general. I want the specific one that goes through that point. Therefore, I'm right on down there, okay? So we're going to move on here, and we're going to do optimization problems. Well, what the heck is an optimization problem? Well, that is where we're going to maximize or minimize something, okay? Lots of times we might want to maximize volume, like in this first example. We might want to minimize surface area. We might want to minimize cost for a company, okay? Lots of different things we can do. And all these problems should look very familiar. We've done them all earlier this year, but we did them all with pre-calculus, not calculus. Now we're going to come back and we're going to do them through calculus. So when I do optimization problems, whoa, almost crossed up. There's a couple things I need to know. There's equations that I must generate. Okay? The first equation I need to find is my primary equation. Okay? Now, typically, your primary equation is going to have multiple variables in it. Could have 2, could have 3, could have 4, could have anything. However, your primary equation, this is the equation that we will want to maximize or minimize, okay? And in order to do that, because some of them have, many of them have multiple variables in them, what we're going to do is we need some secondary equation. Sometimes I need more than one. And these secondary equations, they are true, okay? Whoa, they are true for a given application. They're true for the given application, And they're going to be used to rewrite our primary equation so that we have one variable in it, all right? Now, there's lots of things you want to go through when you are doing these optimization problems, to be completely honest with you. One of the first things you're going to want to do, in my estimation, is probably make a picture. Okay, because pictures really help us understand the situation going on. So we're going to be looking here, we have 24 feet of fence used to enclose a rectangular area using a barn as one side of the pen. So I can say, okay, well, here's my barn, and that barn is going to use it, so here is going to be my pen, all right? So I need three sides here. And we want to, in the end, find the dimensions, okay? Find dimensions that will maximize the area of the pen. So after we make sense out of a picture with it, okay, what we're going to want to really do is we're going to want to, number 2, find our primary equation. And our primary equation, like I said before, this is exactly what we are going to be maximizing or minimizing. Now here we're going to maximize the fun zone for the cows to play in. Well, obviously this pen, okay, if it has three sides, one side being the barn, it must be a rectangular region, okay? So I know my area of a rectangle is length times width, okay? So I'm going to say, here is my width and here is my length. And yes, we can do this in one variable, but I want to start with a couple easy problems so you see the process that we need to go through. Obviously, area equals length times width. I don't know either one of those, okay? So after we're going to do that, and I have two variables, well, I need this in one variable because remember, if we're looking for maximum or minimum of something, we're going to be finding the derivative. When the derivative is 0 or undefined, to find those high or low flat points on the function. Well, area equals length times width, that's a multivariable problem. So the next thing I'm going to do is I'm going to find a secondary equation. Okay? And my secondary equation in this case is pretty simple to come up with because I know I'm going to be using 24 feet of fencing to make up these three sides. So it's kind of like thinking of a perimeter, right? Well, I know 2 times my width plus my length, I'm going to be using 24 feet of fencing. Hey, there's my secondary equation. Okay, so here's primary. And there's my primary. Here's my secondary. Okay, that's my secondary one. So what we're going to do is obviously we're going to have some choices here. Okay, I need the dimensions of this thing. Well, check it out. I can take my secondary equation and I can solve it for either W or L because what we're doing is we're creating a system of equations here, okay? And our secondary equation we are always going to use to substitute into our primary equation. So our primary equation is going to be in terms of one variable. Well, you have options, okay? I could say the length equals 24 minus 2 widths, or I could say 2 widths equals 24 minus the length, and I could say the width is going to equal really 12 minus L over 2, and we want to pick the path of least resistance. Hopefully we see this is going to be easier to substitute in than this. This one's not going to be probably quite as nice because now I'm going to have a fraction, and let's face it, if we don't want a fraction, we don't want to use it. So I would recommend solving for the easier of the two variables, which is obviously length in this situation. So then what we're going to do when we rewrite it, we have our area. Well, my length is going to be 24 minus 2W, and that's going to get multiplied times W. So check it out. I just wrote my area in terms of knowing the width. So I've rewritten it in terms of one variable, my area in terms of width. Well, that is what we want to maximize. So my area in terms of width is actually going to equal 24W minus 2W squared, right? And as I'm coming through, if we want to maximize or minimize something, we're deep enough into our calculus that we know we need to find the derivative and critical points, because we want to see, am I maximizing or minimizing? I need to see that change from increasing or decreasing. And I guess I should have started this whole thing out with, please understand, all three of these problems I'm doing right now, they are non-calculator active. We don't need our calculator for this, okay? There's other times we will, but we don't. So my area prime is going to be what? 24 minus 4W. Well, what's the point of that? Well, point to find maximums and minimums, I want to find out when does my area prime of W, when does it equal 0, and when does this not exist? Well, nice thing is, not applicable here, okay? Because again, we're starting with a polynomial, but we do know 24 minus 4W equals 0. 24 equals 4W when W equals 6, right? So that W equals 6, that's a critical point. That's a critical point. And to find maximums and minimums, every time, didn't we take our critical point, didn't we put it on our number line or our A prime of W line? I only have one critical point here of 6. And if I test both sides of it, okay, into my derivative, now notice I'm probably going to want to maybe take, I don't know, maybe 3. And if I put 3 in there, 24 minus 4 times 3, well, heck, that's positive, isn't it? So I know I'm increasing there. I'm 0 at 6. And if I pick something bigger, like maybe, I don't know, 10, well, what's 24 minus 4 times 10? Well, that's 24 minus 40. Hey, I'm decreasing. So I can see on my number line, my function's going to be increasing, and then it's going to be decreasing. So I have a maximum when what is that? When W equals 6. And I also need to make sure that what I'm going to do, okay, is answer my question in the end. So if I'm coming back here, I'm going to say rewrite primary with one variable. Okay, then after that, I'm going to take derivative of primary and find the maximum or minimum. And then the last thing I want to make sure I do is answer problem. Okay, I'm going to answer the problem. Well, the problem wants to know what are the dimensions. Well, if I know the width equals 6, okay, can't I take that width, plug it into my secondary equation over here and say, oh, okay, then the length is going to be 24 minus 2 times 6. So I know my length is actually going to equal 12, right? So my dimensions, in the end, okay, dimensions are going to be a width of 6 feet and a length of 12 feet. That is going to maximize the fun zone for the cows. And yes, we did use calculus to justify it's a maximum. It's right there. It's on my first derivative test. All right. So we could do that with one variable, but we're going to cruise through it writing a system. Okay. So now number 2. An open top box is made by cutting out congruent squares of side length X from the corners of a 20 by 20 sheet of tin. Find the size squared to be cut out to maximize volume of the box. Okay? Well, I guess I need to think of how the heck do I find the volume of a box? Well, volume of rectangular prisms, whether it's a triangular prism, a rectangular prism, whatever it is, it's the volume, okay? Remember, volume equals area of base times height. Well, if I have a rectangular prism, okay, well, it's going to be length times width times height. But let's get a focus on what's going on here, okay? I have a square sheet of tin who happens to be 20 inches by 20 inches. And what we are going to do is we are going to come in and we are going to cut congruent squares out of here. We did this exact same problem in Algebra 2. We did this problem, you did the problem like this in pre-calc. So we're cutting those out. Then in the end, what we're doing is we are going to fold it along this line. So I have a box. And remember my box, what's the box going to look like? Well, my box is going to kind of, I'm going to have to move this guy over a little bit. Hey, that worked out nice. So here's my box. My box is actually going to kind of look like here, here, and come back. This is going to come back. That's going to kind of come down. And in the back, it's going to kind of come down. Come here, and it's going to come to that corner. Come across. And that didn't work out very well right there. And coming back to there. And there's my box. Isn't that a nice little box? It's a sweet little box. And I know to find the volume of that thing, well, I'm going to take width times length times height. I know volume equals width times length times height. Length times width times height, however you want to deal with it, okay? Well, notice, when I took these corners out and I folded it up, it created this box. Well, what the heck is my width, length, and height? Well, I don't know. When I come down here, I'm actually going to have 3 different secondary equations, to be honest with you, because I know in this case, we're cutting x's out of the corners, right? So when we cut that corner out, notice the height we cut out there, okay, x actually equals h. And my width is going to be kind of across this front leg. Well, that's going to be 20 minus 2 x's. Okay, so I know 20 minus 2x, that's my width. And I know my length here, because it was a square, hey, that's going to be 20 minus 2x as well. So 20 minus 2x, that's my length. So I can take all 3 of these, and I can rewrite that into one function. Okay, so I can see in the end, my volume in terms of x in this case is going to be 20 minus 2w times 20 minus 2, why did I say w? It's not w, it's 20 minus 2x. It's 20 minus 2x. I'm just going to get rid of that. So it's 20 minus 2x times 20 minus 2x times my height is x. Well, there it is. I can, oh, it's a cubic. I don't know if you remember doing this in Algebra 2. We had that copper planter box, right? So what we need to do is I have my volume function here now, and now I want to take the derivative of my volume. So this is my primary equation over here, prime area, okay? And that's what we want to maximize or minimize. Well, boy, I'll tell you what, that's a triple product. So what I think I'm going to try to do is I'm going to try to redefine my volume a little bit here so it's a skosh nicer. So my volume in terms of x is actually going to equal 400 minus 40, what would that be? I guess that would, 40, that would be minus 80x, right? And then it's minus 2x squared. That's still times an x.
So my volume in terms of x actually is 400x minus 80x squared minus 2x to the third.
Okay, well, it's kind of an ugly one.
To be honest, it's mistake, plus 2x squared. So what most people like to really do is take their volume and say, oh, that's 2x cubed minus 80x squared plus 400x, because lots of people are like, hey, I like that little bugger in descending order. There is my primary equation. And that primary equation, no pun intended, is in prime time to find its derivative, because it's a polynomial. Isn't that nice? Just got to take, it's really going to be 6x squared minus 160x plus 400. Yikes. You thought you said this is non-calculator. This is non-calculator, guys. So what we're going to first see is now we need to find out, hey, when does v prime of x, when do u equal 0, and when does v prime of x, when does it not exist? Well, not applicable here again. Kind of funny that happened again. It's a polynomial. So what we're going to do, hopefully we see there's a greatest common factor here. And, oh boy, back up the train here, Kruger. You got this all screwed up. Okay, so we're going to back it up, because negative 2x times negative 2x, that's 4x squared, is it not? So all those got to change to 4s. Oh boy, hate to really back up the train like this, but I need to, because I screwed it up. So that's 4x squared, that's 4x cubed now, which makes this 4x cubed there, because you know, it's just not going to work if we do a stupid algebra mistake in our primary equation, because that's the first calculus involved. Okay, and if I'm not taking the derivative of the right number or the right equation, I'm kind of, well, I better not use my analogy. It's not school appropriate. So now I can see, yeah, I think I got a greatest common factor of 4 in here. So that's going to give me 3x squared minus 40x plus a hundo. Ooh, a nice little hundo. Why won't that thing come off there? Oh boy. Escape. I'm just going to leave it there. I don't really care. And we got to set this thing equal to 0 yet, right? We haven't found that. Well, I know it's got to be 3x times x. I know my last sign is positive, which means the middle sign tells me they're both negative. And I need factors of 100 that when I take one of the factors times 3 and the other one times 1, and I'm going to put them together, I'm going to come up with 40. How about 30, negative 30, negative 10 gives me negative 40. Nice. Factored out really nice. That's what's going to happen when it's non-calculator, guys. That's what's going to happen. So I can see my zeros are when 3x minus 10 equals 0. So that's really x equals 10/3, and when x equals 10. Now, what we really need to make sure we're focused on is, can I really have a critical value of 10? Well, if I came up here, and if x was 10, okay, and this x is 10, well, that just means I really have 4 sheets, and I don't even have a box, do I? Okay, and this is going to work itself out, but you really need to keep in mind this is not in the domain of application. Okay, that's kind of important. It's going to work itself out in this problem, though, because I can kind of really see, technically, I only have one critical point, okay? So I'm going to take that one critical point of 10/3. And if you're like, well, I still don't understand that 10, okay, throw the 10 on the line. It really doesn't matter because we're maximizing, right? We're maximizing, no, is that what we're doing? I think that's what we're doing. We're maximizing volume. So we need to see a change from positive to negative, don't we? So if I come back here, 10/3, I don't know, I'm going to say maybe 1. I'm going to test 1 in there. I know that's smaller than 10/3. Well, 4 is always positive. And if I put a 1 in here, this factor is negative. If I put a 1 in here, that factor is negative, which means that's going to be increasing. Okay? I know 5 is bigger than 10/3 and it's smaller than 10. And that's going to be positive. If I put 5, that's 15 minus 10, so that's positive. Put a 5 in here, 5 minus 10, that's still negative. Positive times a negative, that's negative. And then if I went bigger than that and said, I don't know, who really cares? We have no dimensions on it. Let's go 20. Well, that's positive. That's positive. And this one's going to be positive. So then I'm going to be positive again. Remember, not in domain right there, which it works itself out because I can see increasing to decreasing, decreasing. Oh, that would have been a minimum anyways. I don't want that. But if I identify it's not in the domain, I don't even need to test it. So I have a max when x equals 10/3 inches. Now, do they want to know the dimensions of the box? Because if they do, I got to find the dimensions of the box. And no, they just want to find the size square to be cut out to maximize the volume. So the size square, hey, that's my height, okay? The size square that I'm cutting out to maximize is going to be 10/3 inches. And I did that all using calculus, okay? One more. And if you're like, oh, I forget all these geometric formulas like in this next one, okay? You need to design a 250 pi milliliter can. Just so you know, 250 pi milliliters is 250 pi cubic centimeters, okay? And the important part here is to see it's cubic, which means we're talking about volume, all right? So you need to design a 250 pi cubic centimeter can, so it's holding a volume in the shape of a right cylinder. What dimensions will you use? We'll use the least material. Ooh. What am I actually optimizing? Am I optimizing volume? No, I'm optimizing, I'm actually minimizing surface area. And if I think of a right cylinder, it's kind of like a can of soup. I know my cylinder has a radius. I know it has a height. But remember, what I want to do is I want to minimize the amount of material to make this can. So surface area, if I really break it down, it's a base plus a base, and both bases are circles, right? Plus, if I cut those two bases off and I slice the side of the can, hey, that just makes a rectangle when I fold it out, doesn't it? So surface area, how do I find the area of a circle? Area of a circle, well, that's pi r squared, plus that's pi r squared, plus I know this is my height right there, right? That's my height. And what is this length right here? Well, that's just the circumference of the top or bottom of the can, isn't it? So that's 2 pi r, because this side's going to be 2 pi r, because that's the circumference of the can, times height. So I can see surface area is going to be 2 pi r squared plus 2 pi r times h. Well, if it makes you feel any better, geometric formulas, even on the AP test, they're going to give you the geometric formulas. Oh my gosh, I mean, I got to remember. No, you don't have to remember this. You have to remember calculus-driven formulas. Geometric formulas will be given to you.
So if you need to know the volume of a sphere, yes, they're going to tell you volume equals 4/3 pi r cubed. They will give that to you, okay? Now, this is my surface area, and that's what I'm trying to minimize. Bless me, self. Minimize surface area. This is my primary equation. Okay? Well, I really can't take the derivative of that thing because it's multiple variable. Okay? I want the dimensions. Well, what else do I know about this thing? Well, I do know the volume of this can. Okay? How do we find the volume? Well, it's area of the base times the height. So area of the base is pi r squared times the height. What do I know about the volume? I do know the volume is 250 pi centimeters cubed. That's what pi r squared h equals. Well, I need to solve this secondary equation to rewrite that. Notice I have an r squared, I have an r, and I have an h. Which one is going to be easiest to substitute in, yet still have a nice equation to work with? Well, h equals 250 pi divided by pi r squared, doesn't it? Well, isn't that really kind of nice? Because when I simplify this, I see these pi's will reduce. So I know h equals 250 over r squared. So I'm going to take that into my primary equation. So I can rewrite my primary equation into something I can take the derivative of. Nice. Okay? So we're going to say the surface area equals 2 pi r squared plus 2 pi radius. And we just redefined the height to 250 over r squared. So check it out. I just rewrote my surface area in terms of the radius, surface area in terms of r. Well, it cleans up pretty decent here if you see. Okay, so as I'm cruising along here, the surface area in terms of radius equals 2 pi r squared plus, well, I forgot my 0 on my 250. So I do see I'm going to have 500 pi over r, because this r is going to get rid of one of those. Right? Hope I did that right. And then I have everything in terms of r, but I don't want to take the derivative of it here. Well, what I could do, actually, if you see, I could push this together and I could take the derivative as a quotient. Don't want to do that. That's too much work. And so let's look at the surface area in terms of radius. That's going to be 2 pi r squared plus 500 pi times r to the negative 1. Let's just power rule this dirty little rat. So my surface area prime in terms of its radius, well, that's going to be 4 pi r minus 500 pi r to the negative 2, isn't it? So I can rewrite this. That's my prime. It's 4 pi r minus 500 pi over r squared. Okay? And I don't know, some people like to get common denominators here. You can solve it right here. Okay? Or I can say my surface area, because it's a rational function now, equals, I can see I'm going to have a common denominator of r squared, right? So if I took this times r squared, what I really get is I get 4 pi r cubed minus 500 pi, right? So I can see, hey, when does the surface area derivative equal 0? Well, that's when 4 pi r cubed minus 500 pi, that's when that equals 0.
And because I have a rational function this time, when does it not exist? Well, hey, that's when r equals 0. Well, if I have a radius of 0, okay, I have a radius of 0, I don't even have a can, so if the radius is 0, my can fit nothing in it. So I know this one right here is not in domain of this application. So I don't even need to test that critical point, all right? But I do need to know I can't use that as a test value for increasing and decreasing. But I do know here 4 pi r cubed equals 500 pi, and I can divide out my pi. For those that don't like pi, 4 r cubed equals 500. Then I can divide out my 4. Yes, I could divide out the 4 pi all at once. I didn't because I didn't want to confuse anybody. So I know r cubed equals $1.25. Oh, didn't I say they're non-calculator? When they're non-calculator, they're going to work out nice, 5 centimeters. Okay? So what do I need to do? I need to set up my test, and I need to make sure my surface area in terms of r, that's my derivative line. Really, I can put that 0 because my radius has to be greater than 0, which was really a critical number, so I can't use it as a test. I'm going to throw 5 in here. Well, when I plug this in, this is kind of hard to read up here. Okay? Well, bottom line, the denominator is always positive. Let's say I put a 4 in here. Okay? So if I put a 4 in there, well, what am I going to be getting? Well, 4, well, that's 4 pi 4 cubed. Well, that's like 4 to the 4th times pi, right? Which is really kind of like 16 squared times pi. So that's really 256 pi is the way I see that. Okay, so if I took 256 pi minus 500 pi, the top's going to be negative, so I'm definitely decreasing. Okay, and then I got to pick something bigger than 5. 6 might be kind of hard. Okay, get out of there. Get out of there. So the next thing, I'm going to jump up to like maybe 10, okay? Because I know 10 to the 3rd power. 10 times 10 is 100 times another 10 is what? Okay? What's that going to get me? That's going to get me 10 times 10 is 100 times another 10. Ooh, that's 1,000, isn't it? So that's like giving me 4,000 pi minus 500 pi. Hey, that's making my top positive. So I had a change from decreasing to increasing. Therefore, I have a minimum when r equals 5 centimeters. Well, that's kind of crafty. Did they want the dimensions of the can this time? What dimensions will use the least? Okay, so what I'm going to do is I'm going to say the dimensions are radius of 5 centimeters, which means my height, I take my radius and I plug it right in here. Well, that's 250 over 5 squared. That's 250 over 25. Hey, that means the height is 10 centimeters. So there are my dimensions of the can. Okay? We're going to call it quits there for today for those 3 problems. Tomorrow we'll probably do about 3 more. And then you should have some good tools to work on over your Christmas break. Have a good afternoon.